Hi, my name is Leah Buechley, and today I'm going to talk to you about 3D printable Play-Doh. This is work done in collaboration with my wonderful student, Ruby Ta. So before I get into the details of 3D printing with Play-Doh, I wanted to give you an overview of the process that we go through. So first, like any other 3D print, the first thing you need to do is to design your part in software. Then once your part is ready to print, you have to prepare the material and print it. So we mix our Play-Doh from very readily available off-the-shelf ingredients. We use a simple kitchen mixer to mix it. We color the dough with standard food coloring into a very wide array of vivid colors. Once we've done that, we can load the dough into a print tube and then print the material on a 3D printer that's designed to work with clay. In our case, we're using primarily an EZOW0 clay 3D printer to do the printing. Once a part is done printing, an important part of the process is to allow the print to dry until it hardens and becomes functional. Once it's dry, you can really use these prints just like you would any other print. But if you're kind of done with the print and want to dispose of it, you have a couple of different options. So instead of just throwing it in the trash, you can actually put it on your compost pile and let it decompose. Or if you'd like, you can dissolve the print back into water to turn it back into a printable Play-Doh material and reprint it. So the paper about this process goes into detail about how we designed a 3D printable Play-Doh material. I'm not going to go into that in this talk, but I did want to share with you the basic recipe that has been the most successful for us. It's made out of corn flour, wheat flour, a little bit of play sand, vinegar as a preservative, vegetable oil, and a little bit of white glue. And then, as I've already mentioned, we use food coloring to give the dough different colors. So I wanted to spend most of my time with you today talking through why we think these materials are really exciting and interesting materials for digital fabrication and design research. The first thing that's noteworthy about them is that they're very sustainable materials. So they're extremely easy to recycle. So once you're done with a print, you can collect all of the waste that might have been produced during the design and printing process, along with any unwanted prints. You can put them into a container and just soak them in water for a few hours. Then you can mix them into a mixture that's the right consistency for printing, and you can easily just reprint that material. So very little waste has to be produced in this printing cycle, and it's very easy to recycle the waste material. Another important component of sustainability that we kind of discovered through working with this material is that it's extremely repairable. So if you print something and it has a crack, or if you print something and it breaks, instead of throwing a piece away, you can very quickly and easily repair it with white glue like Elmer's glue. So in this example, you can see this is a Stanford bunny print, but the ear broke off. We can just apply a little bit of Elmer's glue to the broken part, put it back in place, wait for that to dry. And then the seam, the repair seam, is virtually undetectable, which you can see here in the image on the right. And then finally, these materials are all compostable. And so if you leave them in a damp place, they will very quickly decompose and just become part of the natural ecosystem. So you can see here's a little experiment that we did. These are 3 3D printed cylinders that we left in a sealed, moist Tupperware container for about a month. And you can see that they've rapidly started to degrade and really function as substrates for other living organisms. All of these features, when you put them together, really enable a 3D printing process that kind of minimizes waste and environmental impact. So first, all of these materials that we're using come from renewable sources. They're very easy to make. You can print things and then recycle things, and that process can go on for quite a long time. If anything is wrong with your print, you really don't have to throw it out. In many, many cases, you can fix it by patching it like you see here, or by gluing broken pieces together, as we've already documented. And then when you're finally done with a printed piece, you can compost it. And as we've discussed already, these things readily degrade and compost. So again, this opens up, I think, new frontiers for sustainable processes in digital fabrication. But we also think there are other really important and interesting design affordances that are presented by Play-Doh. So another important one is the accessibility and speed, we'll call it. So first of all, this material is really inexpensive and easy to make. So flour, a little bit of glue, sand, and food coloring, and you're set. You can just mix this all up in a kitchen mixer and print it. So this material creation part is super easy and accessible, super cheap. And then another thing that we think is really significant is that you can produce interesting, beautiful parts very, very quickly. So the example you see here on the right, this is a textured vase that's about 4 inches high. This took us a little over a half an hour to print. And this same part at that same scale would take about 10 hours to print if you're working with a traditional fused fabrication machine and working in a material like PLA or ABS. So we've essentially decreased by an order of magnitude the amount of time that it takes to 3D print things. And why I think this is so compelling is that it enables us to do 3D printing in contexts in which we simply couldn't explore that kind of activity in the past. Think in particular about group settings, kind of places like classrooms or after school clubs. All of a sudden, doing a activity that is revolves around 3D printing is made much, much more feasible to do. So we're really excited about this aspect of the material. But we also have found the material to just be a really compelling material in and of itself for a number of reasons. Perhaps the most compelling one is how wonderful it is to be able to work so quickly and fluidly in full color. So it's very easy to design and make your own full color filament with this material. And the way you do that is you mix up some Play-Doh and then you dye kind of different batches of the dough in different colors. And then you can stack up different colors of dough in your print tube. And then as you print from that print tube, those colors will stack up in your part, and you'll get this beautiful gradation from one color to another, as you see in this example. Our custom software, which is also described in detail in the paper, allows you to map colors to different areas of your print, and you can do things like map different computational components of form to different colors. It's low resolution, but nonetheless quite meaningful. So here's a very simple example. This is a data physicalization example where we're visualizing yearly temperature data for 3 different United States locations. And here we're using a red color to correspond to hotter temperatures and the hotter months of the year, and a purple color to correspond to the cooler months of the year. Share just a few other prints that were made full color in Play-Doh to get a sense of the possibilities. This one is a favorite. Just love the way it has this character, almost like a woven basket. So color is wonderful, but we also think there are a lot of other really interesting material possibilities that can be explored here. So I'll talk about a few of them. So one is that it's possible to combine Play-Doh and other materials in a single print, particularly if you have a dual extrusion printer. One example that we've been exploring is to use Play-Doh as a 3D printable support material for ceramics. And so you can combine ceramic 3D printing with Play-Doh 3D printing, and that's a powerful and interesting combination. So currently, there are no viable support materials for 3D printed ceramics. Unfortunately, ceramics dissolve in water, so none of the traditional approaches work. But what we do is we use Play-Doh as a support material for ceramics because it burns. It doesn't dissolve, it burns. And in particular, it burns when it's placed in a kiln. So for example, here, Play-Doh is serving as support material for the handle of this 3D printed ceramic mug. When the print is finished, we take the whole, both Play-Doh and ceramic print, put it in the kiln. The Play-Doh burns away and leaves just the ceramic components behind. We're also really interested in exploring the possibilities that are afforded by the sustainability of a material like Play-Doh. So as we've already described, Play-Doh kind of rapidly degrades when it's placed in a context like a compost pile. We're very interested in exploring kind of the design possibilities that are opened up when working with a material that can be in dialogue with the natural world in all sorts of interesting ways. So on the left, you see a print that is kind of covered with this lovely fuzzy mold. We're really interested in exploring the design potential in processes of decomposition with materials like this. On the right here, you see a more macro scale of a different kind of decomposition. So here, this is a print that collapsed and then was left in the studio for a period of time. And ants came and ate away at the print, making this network of tunnels through the material. And this was unexpected, but delightful. And again, I think suggests a whole very interesting set of design possibilities where we collaborate with natural systems to design and build digitally fabricated / naturally fabricated artifacts. So really just in conclusion, we see Play-Doh in particular, but also materials like Play-Doh that might be developed as opening up a whole host of really exciting possibilities in ongoing digital fabrication work. And we're excited to explore them. So thank you very much.